In May 2004, Intel canceled two processors, codenamed Tejas and Jayhawk, and reassigned the design team. 5 months later, in October, it canceled the 4 GHz Pentium 4 itself.
And that second one is the number to hold on to. The fastest Pentium 4 Intel ever shipped ran at 3.8 GHz. The 4 GHz desktop chip everyone was waiting for simply never arrived. And for about 30 years before that, the deal had been simple enough that most people never thought about it. Wait 18 months, buy a new computer, and the same software runs faster. You did nothing. The machine got quicker underneath you.
That deal ended in the mid-2000s, and it ended on physics rather than on ambition or competence.
Which is worth saying clearly, because the usual telling makes it sound like somebody failed. Nobody failed. The engineers were not worse than the previous generation. They ran into something in the material itself that no amount of cleverness was going to argue with.
And the industry experienced it as a wall.
It was a wall for almost everything. Except that the thing they built instead, to get around the wall, turned out to be exactly the machine one particular idea had been waiting for since the 1950s.
Nobody planned that. That's the episode.
Quick note, this is education, not advice of any kind. AI moves fast, so treat it as a map, not gospel, and go try it yourself. Quick callback, one line each. Episode 1. The idea arrived before any machine could test it. Episode 2. When the machine couldn't test an idea, the field started reading untestable as refuted. Episode 3. The machines finally arrived, purpose-built, one in public, and still didn't generalize because the judgment inside them was handmade.
So in all three, the hardware is either missing or wrong or too narrow.
And in this one, it finally shows up. But here's what makes it different from episode 3. Nobody built it for this. Deep Blue was built to play chess. The Lisp machines were built to run Lisp. The machine in this episode was built to draw video game graphics, and it was mass-produced because of a failure in an entirely different part of the industry.
So the loop closes by accident.
By accident. And the spine of the episode is that sentence, an industry-wide retreat, forced by physics, aimed at gamers, produced the hardware a 20-year-old idea needed. Which raises an uncomfortable question we'll come back to at the end. How would you ever plan for that?
Let's start by fixing the thing almost every version of this story gets wrong. You'll hear that Moore's Law ended.
It's the wrong law. And this isn't pedantry, because naming the right one changes what the failure actually was.
So what is Moore's Law precisely?
Moore's Law is about transistor count. Roughly, the number of transistors you can economically put on a chip doubles on a regular cadence. Gordon Moore first wrote it down in 1965, looking at about 5 data points, and revised the cadence a decade later. It is an economic observation about manufacturing, not a law of physics. And it kept going. It kept going for years after clock speed stopped rising, and arguably it's still limping along now.
Then what broke?
A second, quieter thing called Dennard scaling from a 1974 paper by Robert Dennard and colleagues at IBM. The observation was that as you shrink a transistor, you can also scale down its voltage and current, so the power per unit area stays roughly constant.
Which sounds technical, but the consequence is enormous.
The consequence is the free lunch. Smaller transistors, more of them, and you can run them faster without the chip melting. Moore's Law gave you more transistors. Dennard scaling is what let you turn them into speed.
So they're not the same claim at all.
They're not even about the same quantity. One is about how many switches you can fit and afford. The other is about how hot they get when you use them. For about 30 years, they traveled together, which is exactly why people merged them in their heads.
So when people say Moore's Law ended, what they actually mean is
the part that gave you free speed ended, the part that gave you more transistors carried on. And that distinction is the whole reason the industry's response took the shape it did. If you genuinely run out of transistors, there is no response. You're finished. But they hadn't run out of transistors. They had run out of ways to turn transistors into frequency.
So the question became, what else can you spend them on?
And the answer to that question is the rest of this episode.
Sit on the old bargain for a second, because it's easy to underestimate how good it was.
Every generation, transistors get smaller, they switch faster, and each one uses proportionally less power. So a chip designer could spend the entire gain on frequency, ship it at a higher clock. Done.
And the software side of that is the remarkable part.
The software side is that you didn't have to do anything. A program written in 1990, unchanged, ran faster in 1995 and faster again in 2000. No recompiling, no rewriting, no thinking about parallelism. The machine simply did the same thing more quickly.
An entire industry's productivity assumptions were built on that.
And it's worth noticing that this is historically weird. In most fields, improvement requires someone to do work. Here, improvement arrived on a schedule, and you collected it by doing nothing. A software company could promise features for next year on the assumption that next year's hardware would absorb the cost.
It also shaped how people were trained.
Deeply. An entire generation of programmers learned to write straight-line, single-threaded code because that was the thing that got faster for free. Parallel programming was a specialist skill for supercomputing people. There was no reason for anyone else to learn it. And that turns out to matter a great deal in about 10 minutes of this episode.
So when the free lunch stops, it isn't only a hardware problem.
It's a hardware problem that instantly becomes a software problem, and then a skills problem. When that stops, everything after it has to be earned by writing different software, by people who mostly hadn't had to.
Which is exactly what happens next, and it takes about a decade. So what actually stopped it?
Two things that arrive together. The first is leakage. A transistor is meant to be a switch, on or off. But below a certain size, off stops being properly off. Current escapes even when the transistor isn't doing anything.
So the chip is burning power sitting still.
Burning power sitting still, and that fraction grows as you shrink. The second is power density, heat per square millimeter. As clock speed rises, switching happens more often, and each switch costs energy. At some point, you cannot get the heat out fast enough.
And there was some fairly colorful rhetoric about this at the time.
There was. People compared projected chip power densities to a nuclear reactor and then to a rocket nozzle. Treat that as period rhetoric rather than physics. But the underlying problem was real, and it was not going away.
Why couldn't they just cool it harder?
Because the heat isn't spread evenly. It concentrates in whichever part of the chip is switching fastest, and you have to move it out through a package that's only so big. You can add a larger heatsink, then a fan, then liquid, and consumer machines did all three, but each step buys you less than the last at more cost and more noise, and none of it changes the underlying curve.
And the result shows up very clearly in the data.
Clock speeds flatten in the mid-2000s and then stay flat. Not for a year or two, for well over a decade. Put a number on it. The fastest desktop part of 2005 ran at 3.8 gigahertz, and today's fastest desktop parts boost a little past 6. That's about 1.5 times in 20 years, against roughly 100 times in the 20 years before. Everything gained since has come from somewhere else.
So what does an industry do when it can no longer deliver the thing it has been selling for 30 years?
It sells a different thing. Moore's Law is still delivering transistors. That hasn't stopped. So you spin them on more cores instead of a faster one. Dual core, then quad, then more.
And I want to be precise about the word forced here.
It matters. This was not a considered strategic bet that the future was parallel. It was the only remaining way to use the transistors that kept arriving. 2 cores at 3 gigahertz fit inside a power budget that 1 core at 6 gigahertz does not, because power scales badly with frequency and roughly linearly with core count.
So it's an engineering surrender, dressed as a product decision.
That's not unfair. And the marketing of the period is quite revealing. The industry stops advertising gigahertz almost overnight and starts advertising core counts instead. The number on the box changes, and the implied promise quietly changes with it.
Because twice the cores sounds like twice as fast.
It sounds like it, and for most buyers it wasn't. That's not really deception. The alternative was to advertise nothing at all. But it papered over a genuine discontinuity in what a new computer would do for you.
And the physics behind why width works and frequency doesn't?
Power rises steeply with frequency. You're paying for voltage as well as switching rate, and those compound. Adding cores costs power roughly in proportion. So within the same thermal budget, you can have 1 core running much hotter, or several running cooler. Once you can't cool the hot one, the choice makes itself.
And here's the part that usually gets skipped, which I think is a mistake, because without it, the ending sounds obvious.
Go on.
For most software, multi-core didn't help very much.
It didn't. And there's a clean reason. Most programs are sequential. Step 2 needs the result of Step 1. You can't do them at the same time no matter how many cores you own. And there's a formal version of that constraint, Amdahl's law, which says your possible speedup is capped by whatever fraction of the work has to run in order.
Give me the intuition.
If 10% of your program is irreducibly sequential, then even with infinite cores, you cannot get more than 10 times faster. Ever. The sequential part becomes the floor.
So the industry spent years shipping chips with more and more cores that ordinary software couldn't use.
Widely experienced as stagnation, and a lot of people said so. At the time, the machines were getting wider, and the things people ran on them mostly weren't getting faster.
And rewriting the software wasn't a realistic answer?
For a lot of it, no. Parallel programming is genuinely harder. You have to reason about several things happening at once, about which piece of data is safe to touch and when, and about bugs that only appear on some runs. And a great deal of valuable software was already written, working, and not going to be rebuilt because processors had changed shape.
So there's an enormous installed base pulling in the opposite direction.
And it's worth being fair to the chip designers here. They did not stop trying to make single-threaded code faster. A lot of ingenuity went into predicting branches, reordering instructions, larger caches. But those are refinements measured in tens of %, not the doublings people had grown used to.
But the hardware wasn't useless.
The hardware was waiting. It just needed a workload shaped like itself. And almost nothing in mainstream computing was shaped like that.
Except one thing was.
Training a neural network is, underneath all the terminology, multiplying very large arrays of numbers together. That's most of it. And the crucial property is that when you multiply two large matrices, every output element can be computed independently of every other one.
So there's essentially no sequential fraction.
Within that operation, essentially none. Which means Amdahl's law, the thing that had been strangling everyone else's speedups, barely bites. Throw more arithmetic units at it, and it genuinely goes faster, almost in proportion.
Spell out why that's true, because it's the hinge of the whole episode.
Take one output number in a matrix multiply. To compute it, you take a row from one matrix, a column from the other, multiply them element by element, and add up the results. That's it. It doesn't need to know what any other output number is. So 1,000 of those can happen simultaneously without coordination, and nothing has to wait.
And a neural network is layers of that.
A forward pass is a stack of those operations. Training runs the same machinery backwards to work out how to adjust the weights, and that's more of the same arithmetic. So the overwhelming majority of the work is the one thing that parallelizes almost perfectly.
So, this is the rare workload that wants exactly what the industry was forced to build.
And now hold that next to episode 2, because it's uncomfortable. The method hadn't fundamentally changed. Backpropagation was published in its modern form in 1986. Convolutional networks were working on real problems by 1998. The idea was sitting there.
What changed was the shape of the available machine.
What changed was that the world accidentally started mass-producing hardware whose shape matched an idea nobody was building hardware for.
And the machine in question wasn't even the multi-core CPU.
No, it was the graphics card, which had gone much further down the same road. A CPU in 2006 might have 2 cores. A graphics processor already had hundreds of small arithmetic units, because that's what drawing images requires. Every pixel on the screen can be shaded independently of every other pixel.
So it was already the right shape.
Already the right shape, already mass-produced, already cheap, because it was subsidized by an enormous consumer market that wanted better-looking games.
So why didn't people use them for other things sooner?
Because you couldn't easily talk to them. Before roughly 2007, using a graphics card for general computation meant disguising your problem as a graphics problem, expressing your maths as textures and shaders, and reading the answer back out of what the card thought was an image. People genuinely did this, and they got real science done, and it deserves credit. But it was painful, and it kept the field small.
And then CUDA.
CUDA's contribution wasn't new hardware. It was access, a way to write reasonably normal programs that run on the card without pretending they're graphics. The parallel arithmetic had been sitting in millions of homes for years. CUDA is the door.
And here's the detail that makes this episode's argument, which I didn't expect. Nvidia didn't build CUDA for machine learning either.
They didn't. In 2007, it was positioned for physics simulation, scientific computing, financial modeling, seismic processing. The machine learning use case was found by users afterwards. So the chain is, the CPU industry fails, the graphics industry benefits, Nvidia opens the door for scientists, and none of those 3 parties is aiming at neural networks.
Which brings us to 2009, 3 years before the result. Everybody remembers.
Rajat Raina, Anand Madhavan, and Andrew Ng published a paper at ICML on large-scale, deep, unsupervised learning using graphics processors. And they said the quiet part out loud. I'll quote it exactly. Our implementation of DBN learning is up to 70 times faster than a dual-core CPU implementation for large models.
70 times. And the baseline matters there.
It matters enormously, and this is a number that gets repeated without its conditions. The comparison is against a dual-core CPU implementation on large models. Elsewhere in the same paper, the range is stated as 12 to 72 times depending on the case. And for a different technique, sparse coding, it's up to 15 times.
So it's not one magic number. It's a range that depends on what you're doing.
Right. And they even put the consequence in the abstract, in their own words. For example, we are able to reduce the time required to learn a 4-layer DBN with 100 million free parameters from several weeks to around a single day.
Several weeks to about a day.
That isn't a speed improvement. That's a change in what questions you can afford to ask. And notice who is saying it. The authors in 2009, 3 years early.
And this is 3 years before AlexNet.
3 years before. The economic case for training neural networks on graphics hardware was made publicly in a peer-reviewed venue before the result that made everyone believe it. Which is worth remembering the next time something looks like it came from nowhere.
So by around 2012, you've got 3 separate things ready from 3 unrelated places.
Methods first, and they're old. Backpropagation, 1986. Convolutional networks doing real work by 1998. Neither is new in 2012.
Second, data.
ImageNet, from a 2009 paper by Jia Deng and colleagues, with Fei-Fei Li as senior author. Millions of labeled images, organized into categories. That simply had not existed at that scale before, and building it was an enormous, unglamorous effort.
And third, the hardware we've just spent the episode on.
Consumer graphics cards with enough memory and enough parallel arithmetic, plus a way to program them.
And the argument you have to make carefully here is about necessity.
Yes, because it's tempting to say the hardware did it. None of the 3 alone was sufficient. Without the data, a large network memorizes the training set. Without the hardware, you can't train a network big enough to need that much data. Without the methods, you have nothing to train. And the ordering was accidental. Nobody sequenced these.
Say more about the data, because I think it's the most underrated of the 3.
ImageNet was a labeling effort at a scale that had not been attempted. Millions of images, each one categorized by a person, organized against a structured hierarchy of concepts. It's not a clever algorithm. It's years of unglamorous coordination. And it was widely regarded at the time as an odd thing to spend a career on.
Because the field's instinct was that better methods mattered more than more data.
Which is exactly the instinct this whole series keeps finding to be wrong. And the AlexNet paper is quite direct about needing it. Their network was large enough that even 1.2 million images wasn't obviously enough. So they augment the data further to stop it overfitting.
So the dataset wasn't just fuel. It was a constraint on how big a model you were allowed to build.
Data, hardware, and method were each other's ceiling. That's why all 3 had to arrive before any of them mattered.
Now the moment. And I want to do this one carefully, because it's the single best piece of evidence in this entire series.
2012. Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton enter the ImageNet competition with a convolutional network. 60 million parameters, 650,000 neurons, 5 convolutional layers, and 3 fully connected layers.
And what did they train it on? Because this is the part people expect to be exotic.
2 consumer graphics cards, GTX 580s, the kind of thing you bought to play games. And here is the paper's own sentence. I'm quoting it exactly because it matters. A single GTX 580 GPU has only 3 gigabytes of memory, which limits the maximum size of the networks that can be trained on it.
And the next sentence?
Therefore, we spread the net across 2 GPUs.
So they didn't use 2 cards to go faster.
They used 2 cards because the network did not fit on one. Speed was a side effect. The reason for the split was a 3 gigabyte ceiling on a consumer gaming card.
And it shows up in the architecture.
It shows up in the shape of the model. The 2 halves don't talk to each other at every layer. Some layers only see the feature maps on their own card, and only certain layers connect across. That restricted connectivity is not a theoretical insight about vision. It's a consequence of a memory budget.
So one of the most influential models in the history of computing has a hardware limitation baked into its topology.
You can read the diagram and see the constraint. That is this entire series thesis with no interpretation required. And how long did it take? The paper says, our network takes between 5 and 6 days to train on 2 GTX 583 gigabyte GPUs.
And the result?
Let's do the numbers properly, because the latter is more interesting than the headline. The network as described in the paper gets a top 5 error rate of 18.2%. Averaging 5 of them gets 16.4. The actual competition entry, 5 of those, plus 2 more pre-trained on a larger set, comes in at 15.3%.
And the field it was competing against?
The second best entry that year was 26.2%, using an approach that averaged several classifiers built on hand-designed features.
So roughly 11 points clear of the runner-up.
11 clear of the runner-up and about 10 points down on the previous year's winner. Those are 2 different measurements, and both are worth having. The improvement from 2010 to 2011 had been about 2.5 points, roughly 28% down to roughly 26. This was around 10 points in a single year, 4 times the normal annual step.
And what happened afterwards is almost as telling.
The following year, the winner was around 11%, then about 7% in 2014. By 2015, around 3.6%, and at that point, the machines had passed the human reference point, which had been measured at roughly 5.1% by having a trained annotator label 1,500 images by hand.
And that human number deserves a caveat.
It does, and it's a good one. That 5.1% is one well-trained person. The same study ran a second annotator who trained on far fewer examples, and that person scored 12%, more than double the error. So human level isn't a property of humans. It's a property of how much training that particular human got, which, for a series about handmade evaluation, is a fairly pointed detail.
So within 3 years of AlexNet, the benchmark was effectively finished.
Which tells you 2012 wasn't a fluke at the top of an existing curve. It changed which curve everyone was on. Every winner after it was a deep network.
Which is why people believed it.
And I'd put it exactly that way. It convinced people because it was a margin, not because the method was new. And I want to actually show that, rather than just assert it. The network's activation function, the rectified linear unit, is credited in the paper itself to Nair and Hinton 2 years earlier. Dropout, the regularization trick, is described in the paper as, their words, the recently introduced technique, citing a separate archive paper from July of the same year. It wasn't formalized in a journal until 2014.
So AlexNet invented neither of them.
Neither one. Convolutional networks go back to LeCun in the 80s and 90s. Backpropagation in its modern form is 1986. What was new in 2012 was that someone put existing pieces on hardware that could finally afford to run them against a dataset big enough to matter. If it had won by half a point, we would probably not be talking about it, and the people who'd been working on this since the 80s would have gone on being ignored for another decade.
So what's the rule?
Deep learning did not need better hardware than everyone else had. It needed enough hardware. And enough showed up attached to a product built for video games, mass-produced because a completely different industry hit a wall.
Which has an uncomfortable corollary.
It does, and it points straight back at episode 2. For roughly 20 years, the idea wasn't wrong. It was under-resourced. We spent episode 2 watching a field read, "We can't run this," as, "This doesn't work." And here's the other side of that same error. The gap between an idea being wrong and an idea being early is often just a number. How much arithmetic you can afford.
And nobody could see that number from inside.
Nobody. Which is what makes the closing question genuinely hard rather than rhetorical. Right now, an enormous amount of silicon is being designed for one workload, deliberately this time. So, is today's hardware converging on a method, arithmetic, that many future ideas could use, or on today's dominant model?
And what would tell us?
2 things, and they're checkable. First, when a genuinely different architecture appears, does it run well on the hardware that already exists, or does it need its own? That's the same question we asked at the end of episode 3, and it hasn't been answered yet. Second, and this one is more in the spirit of tonight, is enough for the next idea already sitting in a product built for something else. Because if this episode is any guide, that's where it came from last time, and nobody recognized it until someone tried.
Next episode, What happens when AI compute stops following the general purpose curve altogether?
When it breaks away from Moore's law entirely and starts setting its own.
That's a wrap. If this made AI a little clearer, hit subscribe. It helps more curious people find the show. See you next time.